we just don't really know where and when floods occur for most of the world. If we wanted to build dams or issue warnings or provide relief without actually knowing exactly where and when these floods occur, it's going to be hard to do those things.
Welcome to VoxDevTalks. My name is Tim Phillips. Today we're focusing on a place that my guest describes as ground zero for the harmful effects of climate change. It's a place that's also featured in our recent episodes with Pranav Bardhan of Berkeley and Asif Saleh of BRAC. Today, hello to Dev Patel of Harvard, who has recently written 2 innovative papers offering new insights into those harmful effects and the impact of the livelihoods of millions of people in, of course, Bangladesh. Dev, welcome to VoxDevTalks.
Hello, Tim. Thank you so much for having me. I'm delighted to be here.
We are delighted to have you, Dev. Why did you describe Bangladesh in this way? It's strong language, ground zero.
Yes, as a PhD student stuck in Cambridge during lockdown, I actually asked myself a very similar question. I wanted to study the intersection of climate change and economic development. And I ultimately decided on Bangladesh as the place that I would go do pilot interviews once restrictions lifted, because I think to me it has this dangerous combination of 3 factors. So first, Bangladesh is incredibly dense, about 170 million people living in an area the size of the state of Georgia, the densest country in the world outside of very small islands and city-states. The spatial nature of climate means that in a setting that's as dense as that one, any given environmental threat is almost automatically going to impact a huge number of people. The second reason is that despite a lot of impressive economic success, Bangladesh remains quite poor. Median consumption today is still only about $5 a day. Third, when we think about the most damaging risks linked to global warming, Bangladesh is really sitting on the front lines. Most of the country sits on the Ganges-Brahmaputra Delta, which, as Pranav mentioned on this podcast, is the largest river delta in the world. As a result, Bangladesh is very low and flat, which makes it very vulnerable to things like floods and cyclones and salinity intrusion. And so it's that combination of density, poverty, and vulnerable geography that made me term it ground zero for climate change's most devastating impacts.
Both Pranav and Asif, when I spoke to them, they stressed that these climate impacts are visible, they're important today. Asif once a year goes and tours that river delta to see these things at first hand. Do you agree with them?
In my survey, I asked about 2,000 farmers, what's the biggest issue facing you? And more than 85% said something about the environment. So right now, even as we speak, there's massive flooding happening in Bangladesh, and more than 5 million people have already been affected.
That flooding is the topic of the first of your papers we're going to discuss today. So, easy starter for you, or maybe not. How do we actually define what a flood is?
Yeah, it's a deceptively tricky question. So
yeah.
I think following both discussions I've had with farmers and what the Intergovernmental Panel on Climate Change says, I define a flood as the unexpected inundation of land that's normally dry. So importantly, in a place like Bangladesh, where there's these monsoon rains and snow melt that cause massive seasonal shifts in surface water, that means that a pond that predictably appears each year, we would not count as a flood under my definition, even if for many months of the year it sits dry.
Okay. It's not just Bangladesh that's affected by flooding. We know that. How many people, how many places in the world are living with this risk now? Is this an increasing risk?
These are incredibly important questions, and ones to which, unfortunately, we just don't have very good answers.
Wow.
So there was a 2022 paper that estimated that about a quarter of the world's population, 1.8 billion people, are facing 1 in 100-year floods. And those authors estimated that 89% of that population is living in a low or middle income country. Other work has also guessed that those are the places where global warming is going to increase flooding the most in years to come as precipitation intensifies and sea levels rise. But there are kind of two important challenges to those results. First is that our existing data on flooding is actually significantly biased, which means that we just don't really know where and when floods occur for most of the world. Scientists often turn to hydrological models instead, but those rely on very strong assumptions about things like soil and riverbanks. And second, so when we think about projections of future flooding and whether it's going to be increasing in the future, it's really vulnerable to what economists refer to as the Lucas critique, which is that, people and governments are just adapting to protect themselves against future floods. My favorite example of this is Egypt used to experience regular flooding along the Nile almost every year, but then they built the Aswan High Dam, and now there's just never been any more flooding for the past 50 years in Egypt. And so dam construction is just one way in which places might adapt to floods. In my survey of farmers, I find that about 60% of them expect flood risk to be lower in the next 10 years. And I think, to be honest, we don't actually have enough data to know whether or not they're wrong.
Right, but one thing that we can observe directly is the consequences of flooding. What are those consequences for people who are effective in low middle-income countries?
This is exactly the question that's at the heart of my paper on flooding. And so what I find are impacts on a host of different dimensions. Using satellite data on nighttime luminosity, which is the proxy for economic activity or a measure of electricity use, I find that floods reduce local brightness for at least 7 years. I also find that the amount of physical space that's occupied by buildings shrinks, again, kind of measured from space, which indicates that there's some important destruction of physical capital and property. I can turn to administrative data, and I find that floods also push workers out of agriculture. They increase intra-household migration. Children attend school at higher rates in the years after a flood. And kind of perhaps most importantly, I find that experiencing more floods in the past actually helps reduce the damage from experiencing future flooding, which points to this important role of endogenous adaptation in mitigating these damages.
Now, it sounds from what you're saying that the data that we have on floods, it's not very complete. It's not very accurate. Maybe you can tell me if I'm right with that. If I am right, it must be very difficult to make any policy based on what we know about flooding.
Yes, absolutely. So when we think about existing flood data, there's typically two types of data. First, there's what's known as in situ data, which effectively involves measuring the height of rivers. So if you were to visit the Bangladesh government website right now to monitor the flood that's occurring on the eastern part of the country, that's exactly the data you would find, is how much above a danger level a river is. But there are two important drawbacks to that type of data. First, in poor countries, there are just very few of these river gauges, especially in the rural, poor places that we might think are particularly vulnerable to flooding.
Of course.
And second is that even if you have that river height data, that's a vertical measure of water. And what we actually care about for flooding is a horizontal one. Converting from that river height to flood coverage relies on a lot of strong modeling assumptions. The second type of data comes from news articles and government reports. Essentially, the New York Times reporting that there's a flood in Bangladesh. And so the most commonly used research data sets are going to be this type of data, the Dartmouth Flood Observatory Archive or the MDAT database. And this is going to be problematic because for floods that are in poor countries, floods that are smaller, and floods that are farther back in time, all of those will be systematically underrepresented in those data sets. In some cases, people use satellite data to kind of supplement those records. So, for example, there's this global flood data that is a very commonly used source on that front. That's more about trying to find the exact extent of surface water, conditional on knowing that a flood existed in one of these newspaper articles. And so a lot of those biases from that sample are carried through. I think for what you mentioned about policy, there's three important ways that this data will translate into policy impacts. First, because we don't actually have a really good sense of where and when floods have occurred, we don't really know what places are at high risk of flooding. So if you went to the Bangladesh government website and you looked at a flood risk map, you would see almost no local variation, even though in practice, we know that can be really important. This part of the river versus that part of the river could actually really matter. The flood risk maps we have are very general. The second is that it actually makes it very difficult to forecast floods and give people proper warning about when they come. So there's this amazing NGO, Give Directly, which I'm sure listeners to your podcast are well aware of. They wrote an amazing blog post last year about their attempts to provide anticipatory cash transfers in Mozambique in the days leading up to a flood. So they partnered with Google, which has a very sophisticated machine learning method to forecast flooding. But for Google, the best data that they have to train their model on is this river height data, which suffers from all those problems we discussed. And so it ended up being that the villages that Google predicted would get flooded received a bunch of cash but never actually got flooded, and different villages did get flooded that never got cash. And so you might think that with better training data, we could have improved that prediction. And the last way with this impacts policy is that we just don't really know a lot about the consequences of flooding and then how we can prevent them. So if we wanted to build dams or issue warnings or provide relief without actually knowing exactly where and when these floods occur, it's going to be hard to do those things.
Dev, you have measured flooding in a completely different way. You mentioned it quickly. Go into more detail about how you did it and how complete your data can be.
So my data and approach combines methods from machine learning and geophysics to analyze satellite data. So I use two types of satellite data. First, I use optical satellites. These take photos of the Earth from space, and they're great because they orbit all the time, so we have tons of photos. But the problem is clouds.
Clouds,
When it's cloudy, these photos can't see the ground. And of course, when is it cloudy? When it's flooding. So for Bangladesh, for example, there are clouds almost every day during the monsoon season. And traditional geophysics approaches will just throw out all of those pictures because they can't see through the clouds. So optical satellites are really great on quantity, but they have this important drawback on quality. The second set of satellite data I use comes from radar. These satellites shoot very light radiation at the Earth and measure how much gets bounced back to the satellite. And so one key feature of those sensors is that when radiation hits surface water, it gets scattered. But when it hits anything else, like land or buildings, it'll get bounced back up to space. And so this ends up providing a very accurate map of where water is on the ground. And crucially, clouds are not a problem for this radiation. The drawback is that those satellites don't orbit very often. And so as I talk to farmers and I ask them about floods that they've experienced that are important, they often mention floods that only last a day or two. And so if a satellite only orbits every 2 weeks, you're going to miss tons of these important events. The key part of my method is to try to get the best of both worlds here, the high quantity of that optical data and the high quality of that radar data. And essentially what I do is I train a machine learning algorithm to replicate that radar data using the optical measures. So instead of discarding a photo because there's a little bit of cloud in it, I let the data tell me whether there's nevertheless any signal about the state of water on the ground across all of those wavelengths that the photo is capturing. And it turns out that there actually is a lot of signal there, and I can recreate that high quality measure quite well. And so when I apply this to days that radar satellite wasn't orbiting overhead, I can get essentially a daily measure of surface water that allows me to let the data tell where and when floods have occurred. I'm in the process of building this out for the whole world, so hopefully there'll soon be a website where researchers or policymakers can download their local flooding data anywhere.
Before we deal with the whole world, though, Dev, let's apply this to Bangladesh, because with this information, you can then look at the impact of floods on any economic measure that we want to think about. But of course, we're not doing this at a national level, we're doing it at a local level. So how granular can your economic data be, and how can you use that to establish a causal relationship from floods going back to the economy? Because, of course, there are many other things changing at the same time.
These are great questions. So as I mentioned, I initially chose Bangladesh because of its importance at the intersection of climate change and development. But it turns out I got quite lucky on the data side. So in the course of collecting their data on vital statistics, which is the basis for things like calculating birth rates and death rates in the country, the Bangladesh government also collects information on education and occupation and migration behavior of its citizens. And so what I did is I harmonized all of those records together, which gives me a data set of about 19 million people over the past 20 years. And for each of those people, I know exactly where they live. And so that's really rare data for a low-income country, but it allows me to get a much richer understanding of the economic impacts of floods. One of the reasons that we've discussed that better flood data is valuable is for policy. From the point of view of an econometrician, though, it's also actually very useful for establishing these causal relationships. And so one key challenge in understanding the impacts of environmental disasters is identifying a proper control group. The spatial nature of climate means that things like droughts and heat waves or cyclones impact huge areas at once. And so it can be very difficult for the researcher to find a comparable control group, especially when you worry about things like spatial spillovers, which means you can't choose somewhere too close, or heterogeneous dynamic treatment effects, which means you don't want to compare places that have experienced disasters pretty recently. But because of flooding has lots of idiosyncratic variation very locally, and my flood measure is so granular, I end up having a huge pool of potential control group places. So I can be very, very strict in how I choose which places to compare flooded places to.
As you say, I don't think you got lucky. I think you've done the hard work here. So what comes out of it? Can we say that there is a measurable impact from floods to local GDP?
Unfortunately, as amazing as many of the data sets are in Bangladesh, we don't have great measures of local GDP. The best I can really do is measures of nighttime luminosity and other things that I can measure from space in order to get the kind of local and high frequency enough variation that I need. But I do find that, at least for 7 years, there is this persistent negative impact of a flood on how bright that place is at night.
This long-lasting impact is 7 years. Is that the length of the impact that you see on agriculture?
That's quite an interesting question. And I think for agriculture in particular, it's a little bit complicated, in part because what we see are impacts on the agricultural labor force that seem quite persistent, but also on children's education, which we might think should impact agricultural employment in the next generation, which I know I don't have enough time yet to observe those, but could be happening. There are also fundamental agronomic impacts of floods on agriculture that can be quite heterogeneous. So to give one concrete example, the amount of salt in the soil is a really important determinant of agricultural productivity, especially for rice, which is the most important crop by far in Bangladesh. So when there's too much salt, the plants can't extract as much water from the soil and they don't grow as well. If you're flooded with salt water, such as tidal surges stemming from a cyclone, then the flood can deposit a lot of salt onto your land, and that can make it salty for a very long time. It takes a long time for that salt to wash away. But there can also be good floods that have fresh water that wash away the salt. And so I think there's still kind of a lot to be learned about the agricultural consequences of flooding.
As you say, this is a surprisingly data-rich environment. Were there other economic indicators that you could apply to this?
I'm currently working on delving more into education, in particular how the kind of short-term versus medium-term versus long-term impacts of floods differ, and then also working on examining more differential impacts by gender. So hopefully I'll have more to share on that very soon.
And are you able to establish the mechanisms behind what's going on, any of the effects that you observe?
My results suggest that experience-driven adaptation is very important in this context. And there seems to be kind of two core mechanisms at play. One is that if you experience a flood, you learn things that make coping with floods easier the next time. So for instance, I may send a family member to the city as an important way that households deal with flooding. And the first time that the family member goes to Dhaka, they have to figure out where to live and where to work. But the second time, things are a lot easier. The second channel seems to be that people's beliefs about future flooding are also different once they've experienced a flood. So you find that people actually think that both the likelihood of future floods and the damages resulting from them go up, which should increase their incentives to adapt in the meantime.
Learning to cope that you were just talking about is the subject of the other strand of your research we're going to talk about today, because in places like Bangladesh, individuals, any group cannot really influence climate change, so they have to adapt. So you also investigate how well farmers are adapting. So what specific question is interesting you here?
In this paper, I really dive into the microeconomics of that climate adaptation decision. I mentioned this danger of soil salinity for rice farmers. So one key technology that farmers can use to adapt to that threat is simply to plant salinity-tolerant seeds. So these seeds are specifically designed so that even when salt levels are high, the plant still grows well. Though these seeds have been around for a long time, not everybody uses them. And one simple explanation is that if a farmer doesn't think that their land is salty, they won't plant that seed and instead will choose a different seed that might be, for example, tolerant to pests or might taste better or might sell for more money. And so that example highlights the importance of what people believe about their environment. And it turns out that we just don't know very much about what those beliefs are, where they come from, and how they might matter.
And from your research, how well do farmers traditionally estimate the salinity of the soil on their land?
I end up finding a huge amount of heterogeneity.
Right.
So some farmers are approximately correct, but there are also a huge share that significantly overestimate and also those that underestimate the amount of salt on their land.
Mm-hmm. And which ones are doing the best job of that?
It turns out that the most accurate farmers are exactly those farmers we might expect to be the most accurate. So the ones that their neighbors think are the best at farming, the ones that have the most land and are the most experienced. One way of interpreting that set of results is that when you have a lot of data, it just makes it easier to learn the truth.
But every farmer has data every year that they could use because they're growing crops every year. So as economists, we would ask why any of them get their estimate wrong at all. Why is that?
So my paper shows that farmers aren't making any mistakes per se, but rather just face a really difficult problem. And it's due to the nature of environmental issues themselves. So a lot of environmental risks are actually just difficult for us to observe. And all we end up actually observing are the impacts of those dangers. Imagine, for example, that you're living in Delhi. You might not precisely know the ambient temperature that you're exposed to each day or the amount of air pollution that you breathed in, but you might feel quite tired at work. That's the symptom. And the problem is that both heat and pollution could make you feel that way. So if you're trying to decide whether you're going to buy an umbrella for shade or buy a face mask, you don't have enough data just from the fact that you feel tired to know whether it's heat or pollution that's making you feel that way. And that same type of intuition applies to farmers trying to learn about salinity. Salt is in the soil just one of the many things that might impact how well your crops grow. And so if all you see at the end of the day is a stunted rice plant, it's hard for you to know whether it's stunted because of salinity or because of a fungus. There are ways to overcome that, for example, by experimenting with different seeds. And that might be one of the reasons that farmers with more experience and more land have more accurate beliefs. But in general, this is just a very difficult problem.
And it's a problem that you used a natural experiment, didn't you, to try to evaluate how farmers respond to events that change the salinity of the soil. How are you thinking about this? What question are you asking here?
Consider a farmer who sees that their crop didn't grow very well this year. Maybe it's because of fungus, maybe it's because of salinity, and that farmer's trying to figure out which one it is. Unfortunately for the farmer, both of those threats manifest themselves in the same way. A plant didn't grow as well. So the question that I try to answer is, how would a perfectly rational Bayesian farmer learn from the fact that their harvest didn't do very well? And it turns out that it all hinges on what they initially think about whether salinity or fungus is the more important threat. If the farmer has a very strong prior that salinity is an issue, then when they see a bad crop, that'll just reinforce their belief. My natural experiment is to try to get quasi-random variation in what people think is the most important threat. I use a very salient shock that people certainly pay attention to and would attribute to salinity, which is specifically a flood with salty water, and a much more subtle shock that could go unnoticed, the intrusion of salt water underground into the water that you use to irrigate. While both of these shocks end up having the same impact on the true amount of soil salinity that I can measure with my agronomic sensors, it turns out that only that salient shock impacts what people think about the saltiness of their soil. And this ends up shaping what they think about the symptoms of salinity in general, in line with that model I described. If you've experienced a very salient shock, that makes you more likely to think that anytime you have a bad harvest, it's a sign of too much salt in your soil.
And so your expectations were confirmed that this is the behavior that you expected and it's the behavior you observed.
Stepping back years ago to when I first started this project, I certainly had expected that most farmers would underestimate salinity levels. And so it was a surprise to me when I found out that that wasn't the case. But I think there's kind of an important lesson in that predominance of overestimation here, which is that when we think about climate adaptation, almost all adaptation measures are costly in some way. If I plant a salinity-tolerant seed, that means I'm not planting some other seed that might have some other appealing features. And so if salinity is actually not as high as people think, we can get over-adoption of climate technology that can be harmful. One lesson from this is that collecting more accurate environmental data is really important. Salinity data is in an even worse state than that of flooding, which makes it really difficult for us to give accurate policy recommendations about salinity to farmers.
And this is a problem that will be experienced by farmers in all the ground zeros around the world.
Absolutely. My project shows that environmental beliefs can often be wrong and can substantially impact important adaptation decisions, and also can be very difficult to learn about on one's own. Although I focus on salinity, one key insight of that learning model is that when many dimensions of the environment are changing at once, as is often the case in these ground zeros, then the learning problem becomes even more difficult. A place like Bangladesh that faces threats from heat, pests, floods, cyclones, salinity, all at the same time, it becomes incredibly challenging for people to accurately learn about each of those risks.
So as you say, these are extraordinarily difficult problems for farmers to solve and to learn about. Is there a policy solution that can help to protect their livelihoods?
One simple but quite cheap and potentially effective policy that I piloted in my experiments in my paper is to help farmers by simply collecting more environmental data and sharing it with them. I find that more than 80% of farmers are willing to pay at least a little bit for a salinity reading on their plot. And what's great news for us is that they actually don't care whether that salinity reading is from their own land or actually just the average of a bunch of plots from the 90 villages around them. Because farmers actually recognize there's a huge spatial correlation in salinity, which means it's really cheap for us then to go and collect salinity readings from a few samples and then provide that information to lots of farmers. There's also a lot of important spillovers from that information. It helps farmers not only learn about salinity, but also about lots of other environmental threats they're facing. And it's an important complement to agricultural innovation and other types of climate-smart technologies.
Faced with a lack of information for farmers, how do we solve this? We give them information, of course. I want to talk a little bit about the methods you've used here, because they're very interesting, very exciting, but somewhat unconventional. Even for development economics now, you've used methods from machine learning, geophysics. Do you think that methods like this are going to become the business as usual in climate economics to solve some of these very difficult problems where we don't have very much information?
That's a great question. And I'll highlight that the brilliant Tamara Carlton and Reed Walker gave some very illuminating insights on this topic when they were on this podcast. I think it's a really exciting time for these methods, but I also am cautious about them. And I think it's important that we recognize their limitations. So for instance, it's really easy for me to go and download rainfall data for every 15 minutes for a rural village in Bangladesh that's based off of a remote sensing model. But in reality, that model is trained off of very few data points in these poor and rural areas. I think there's a lot of complementarity between different types of data. And my hope is that even as remote sensing becomes even more prominent, we don't neglect the investments on these high quality ground truths as they were.
What you do seems to be very policy relevant. When economists are analysing these types of problems, do you think, given the very real and the very urgent nature of the problems, is it always important to be policy relevant in this way?
I'm not sure I'm the best person to answer this question, to be honest, but that a lot of these topics at the intersection of environment and development, there is still a lot of what I might call basic science to be done. Hopefully that work eventually does have policy relevance down the world. That might not be that obvious in the short run, and I still think it's quite valuable to just understand what happens in the world when these types of threats occur.
What you're doing seems to be valuable and interesting as well, Dev. Thank you very much for talking about it.
Thank you very much, Jim, for your very kind words.
The two papers we've been discussing, one is called Floods, one word, Floods, and the second is Learning About a Warming World, Attention and Adaptation in Agriculture. Dev Patel is the author of both of them. This has been a VoxDevTalk. The best way to make sure you don't miss an episode, subscribe. You'll find us wherever you get your podcasts. Leave us a review as well, and then other people can find out about conversations like this one.